Hello everybody and welcome to the Maths Skills lesson on expressing numbers. Now in this lesson we're going to cover three topics. Firstly we're going to look at significant figures, then we're going to look at standard form, and then finally we will look at the SI prefixes. Now, expressing numbers is one of the sort of soft skills for A-level physics that sometimes isn't explicitly taught, but we do just need to make sure that we know exactly how we're expected to write down a number at the end of a question, at the end of a problem. Now, just to get you started, hopefully for this lesson you've got a calculator with you. If not, please just go and get one quickly. First thing I want you to do on your calculator is just calculate the square root of 11. Now, with most Casio calculators, what you'll then see on the screen, if you just put in the square root of 11 and press equals, is your screen will show you the square root of 11 rather than giving you a decimal or something like that. Now, in order to fix that straight away, we're going to use this button here, which is labelled S, and then a double arrow and D, and what that stands for is surd to decimal. In other words, it's going to convert our surd with our square root into a decimal. So if you press that on your calculator, what my calculator tells me as a full answer is 3.3166247.9. Now, of course, that number will go on past that last digit, past that digit 9. Square root of 11 will go on for a long time, in fact, because we're taking the square root of a prime number. It is irrational and will therefore go on forever. Now, in physics, we never want to leave an answer in terms of a surd, square root, and we definitely don't want to give an answer which is in theory to an infinite number of significant figures. Now, in physics, the general rule is that the answer is given to the same number of significant figures as the question is given. So if we look at the question, well, the question was the square root of 11, and we can see that that is given to two significant figures. Therefore, our answer as well must also be given to two significant figures. Now, the second significant figure, or at least the cutoff for it, is there in between the 3 and the 1. So count the significant figures. There's our first one, there's our second one, and there's our third one, etc. If we were to express this to two significant figures, of course, we always need to look at the third one to see whether we need to round the second one. Normal rounding rules apply, so if it's 0, 1, 2, 3 or 4, we will keep the second significant figure the same, we'll round down. If it's 5, 6, 7, 8 or 9, then we're going to round up. So in this case, the third significant figure is a 1, therefore we don't need to round the second significant figure, and therefore in physics we will write the square root of 11 to be equal to 3.3. Now, just to give you a second example on that, if we now do the square root of 139, again, if you just tap that quickly into your calculator, press equals and quite lightly press the S to D button, what my calculator tells me is the following. So it's 11.7898261.2. Now again, 139 is a prime number, so I know straight away that we're dealing with an irrational number again. The question here, 139, is given to three significant figures, and therefore our answer must also be given to three significant figures. As usual, we split off between the third now and the fourth significant figure, but we note that the fourth significant figure is an 8, and therefore we need to round up. So we end up with the square root of 139 is equal to 11.8. So there's our answer given to three significant figures exactly the same as the question. Now, of course, there will come times where you have to use various different constants in physics. One of the classic examples, of course, which we get and we use quite a lot in maths, is pi, which we know from maths is an irrational number. Again, it's a number that goes on forever and doesn't have an end. Now, just to give you an example, if we take a circle and we have a circle with a diameter of 2 meters, and let's say that we want to calculate the circumference of the circle. Okay, so the circumference, different people do it in different ways. We can either use 2 pi r, but of course, because we've got the diameter already, we might as well just use pi times the diameter. Now, when you put that into your calculator, you will do 2, and then you will use the pi button. And in order for you to get the pi button, we press shift, and then pi is there, so we press the times 10 to the x button to get pi, and hit equals. And yet again, most calculators will then give it you in terms of pi, but we can then press the S to D button to get the full answer, and then our calculators will tell us 6.283, etc. I won't go on for there because we know full well that we're going to end up rounding. Now, this is an interesting question because all I've given you is 2 meters and asked you to work out the circumference of the circle. Of course, in the question, the number 2 is only to one significant figure, and therefore the circumference of this circle should then be rounded to 6 meters. If, of course, I'd given you the diameter to be 2.0 meters, then suddenly I've introduced that second significant figure, and our answer in that case would have to be rounded to the second significant figure. Remember, your third sig fig is an 8, so therefore that will be rounded to 6.3 meters. Now, of course, we are never going to give in physics a final answer in terms of pi, so we wouldn't write that the answer is 2 pi meters and leave it like that. We're always going to hit that S to D button to get it into a decimal and round it to an appropriate number of significant figures. If, however, we then need to use that number later on, so we need to use 2 pi later on in another calculation, it is okay to keep that full calculator answer when you're going on to another question. So to give you an example of that, let's use exactly the same circle again. But let's imagine that you've got a question which is telling you that some kind of object is moving in a circle, and it's going to do 4 rotations of the circle. And how far has that object moved? Now, of course, if we were to go back to either one of these answers, let's say that we took this first answer of 6 meters and then multiplied that by 4, we would end up with an answer of 24 meters. If we were to use our value of 6.3 meters and then multiply that by 4, we would end up, our calculator would tell us 25.2, but of course we would then round to 2 significant figures, which would be 25 meters. Now, at that point, you notice that we've got a bit of a problem. Depending on how we've rounded the previous answer, we get a different final answer. If we rounded the previous answer to 1 significant figure, we get 24 meters. If we round it to 2 significant figures, we get 25 meters. So we've got a little bit of a problem here. Of course, we can rectify that by keeping the exact answer as we work through. So the calculation that we're doing is 4 rotations of 2 pi per rotation, which of course is 8 pi. And when we put 8 pi into our calculator, we end up with 25.132, etc. Now, when we round that to 2 significant figures using the 2.0 meter, we end up with an answer of 25 meters. So as I said, it's perfectly acceptable to use an exact calculator answer, in this case 8 pi, or indeed to use pi itself as we're working through our calculations for a final answer. And we can see that if we round too early, we end up with an answer such as 24 metres, which is not the correct answer once we've done our final rounding. Next then, let's have a look at when we would use standard form. Now at this point I'm going to assume that you've been taught standard form at GCSE, and therefore you're happy with how standard form works. Now once again, in your calculator, if you could just very quickly do for me please 174 squared. Now the answer that we get there is 30,276. Now before we go into the rounding conversation, firstly we're going to start talking about standard form. Now the rule of thumb is that as soon as we get above 1,000, in other words, as soon as we get above 10 to the 3, we start to use standard form. If we have a look at this answer then, we can do standard form 1, 2, 3, 4, and we could therefore write that answer as 3.0276 times 10 to the 4. Of course, at that point we're going to round again, noting that the question is in 3 significant figures. Our third significant figure ends there. Our fourth significant figure is 7, and therefore we're going to round to 3.03 times 10 to the 4. We can do another example with 74 squared, which again on the calculator is 5,476. Again, we're above 1,000, so at that point we're going to use standard form. We have 1, 2, 3, and therefore the answer would be 5.476 times 10 to the power of 3. Once again, with rounding, here the question is in 2 significant figures. The answer will be given to 2 sig figs, and therefore we end up with 5.5 times 10 to the 3. If we take one final example here of 24 squared, the answer to that is 576. Now because we're below 1,000, we're going to leave that answer as 576. I have seen some people try to write that as 5.76 times 10 to the 2 times 10 squared, but that isn't really convention, so we're not going to do that. We're just going to leave the answer as 576. Don't forget, of course, to round it, and then the answer, once rounded, is 580. Now, of course, the same is going to work when we have small numbers. So if I give you, again, a quick example, I will just say we're going to convert 2 millimetres into metres. Now, of course, to convert millimetres into metres, we're going to divide by 1,000. When we do that on our calculator, depending on depending on how good your calculator is, some of them may automatically give it in standard form, but some might tell you that it's 0.002 metres. Now, when we're dealing with small numbers, the rule of thumb becomes as soon as we use the thousandths place holding, we're going to start to use standard form. So at that point, instead of 0.002, we will write that as 2, 1, 2, 3, times 10 to the minus 3 metres. If, of course, we were doing a centimetres to metre conversion, so let's say we're doing 2 centimetres into metres, where we are dividing by 100, the answer becomes 0.02 metres. And at that point, because we are using the hundredths placeholding, we're not going to bother converting into standard form. So again, the temptation might be to say, well, 1, 2, we're going to write that as 2 times 10 to the minus 2 metres. But again, because we're not hitting the times 10 to the minus 3, we wouldn't write it as that. We would just leave it as 0.02 metres. So therefore, just to sort of summarise the general rule that we're going to use, if we imagine a number line with powers of 10, so 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3, 10 to the 4, etc., and going down the other way, 10 to the minus 1, 10 to the minus 2, 10 to the minus 3, oh, sorry, not put the minuses there, and 10 to the minus 4. In general, as soon as we get outside 10 to the 3 and outside 10 to the minus 3, we're going to use standard form. Obviously on both sides. But if we have any number which is in between there, okay, so in between 1,000th and 1,000, we're just going to express that number normally without standard form. Now, at A-level physics, you will quite often see and hopefully use the SI prefixes. We use the SI prefixes when we get into standard form territory. So as you can see, when we get above 10 to the 3 and below 10 to the minus 3 in terms of numbers. Now on the screen I've shown you all the ones that do exist. These are all the commonly used SI prefixes. At A-level though, what you're expected to know for the big numbers is from 10 to the 3, so from kilo up to 10 to the 12, which is tera, and then for the small numbers 10 to the minus 3, which is milli, down to 10 to the minus 15, which is femto. The rest of them that you see there, as I say, they do exist, but we tend not to use those necessarily in A-level physics. Now, just to give you an example of where we would use SI prefixes, I've just put a question on the screen. So an object of mass 560 kilograms is subject to a force which causes it to accelerate at 30 meters per second squared. Calculate the magnitude of the force. So this is a relatively easy question. Pause the video quickly and just get the answer on your calculator before we move on. Now, of course, the equation that we're going to use here is Newton's second law, which is F equals ma, or at least that's the simple version of Newton's second law. When we put the numbers in, so we have 560 multiplied by 30, and on our calculators we end up with 16,800. Now, of course, if we go back to the previous conversations that we've had, the first thing we're going to do is to convert that into standard form, which will be 1, 2, 3, 4. So that will be 1.68 times 10 to the 4. Secondly, we're going to just round this. This number here, 560, is given to two significant figures. So once again, we end up with 1.7 times 10 to the 4. And of course, we put our units on the end, which is newtons. Now, if you were to give that answer to 1.7 times 10 to the 4 newtons, that would be absolutely fine. There is nothing wrong with that. However, you can also use the SI prefixes in order to give the answer to your question. Now, of course, the thing you'll notice with the SI prefixes is that they go up in powers of 10 to the 3, so 10 to the 3, 10 to the 6, 10 to 9, and the same the other way, 10 to the minus 3, 10 to the minus 6, 10 to the minus 9, etc. Now, this number here, 16,800, we can write this in standard form as 16 16.8 times 10 to the 3. Now, I know that in standard form that isn't necessarily the way that we would write it as a final answer, but it's okay just to use that as an intermediate step. Now, because we've got a 10 to the power of some multiple of 3, we can now go back up to the SI prefix table and select the correct SI prefix, which in this case would be kilo. That can then be written as 16.8 kilonewtons. But of course, if we wanted to round that to the correct number of significant figures, which in this case is 2 sig figs, then we would write that as 17 kilonewtons. Now those two there do say exactly the same thing, just in a slightly different way. 1.7 times 10 to the 4 newtons and 17 kilonewtons is exactly the same, as I said, just slightly different ways of writing it. Either of those answers would be perfectly well accepted. There isn't really a preference. Personally, I always lean towards the SI prefix version rather than the standard form version. But again, at the same time, I know plenty of people who would rather do the standard form version. And as I said, when it comes to exams, when it comes to expressing yourself in physics, there's absolutely no preference. Either one of those will do, and either one of those will be accepted. Now, just to show you another trick with the calculator that we can use. Once again, if we just use the question that we use on the last screen, we know that our calculator tells us 16,800. Now, at that point, we can use this button here, which says ENG. And what that will do immediately is convert your answer into the style of an SI prefix answer. So if you still have that answer on your calculator, fine, press the ENG button now. If not, just get that answer back on your calculator and hit that button. And what my calculator then tells me is 16.8, and then it has in that style there times 10 cubed, and straight away we've got an answer in the correct format ready for our SI prefix. What we then need to do, either from memory or by coming back to the table and having a look, is we just need to select the right one. So the calculator tells us that we're 10 to the 3. We come back to the table and look up 10 to the 3 for kilo, and we end up with, as we said before, 16.8 kilonewtons, or obviously, if we round that correctly, 17 kilonewtons. Now, just as a final couple of notes on the use of SI prefixes, it's fine to use them with pretty much all of the units. We do, though, have a couple of exceptions, and it normally comes with the base unit, with the second, the metre and the kilogram. Now, firstly, the kilogram. Well, the kilogram, it's a bit of a strange one, really, because it's already got the kilo in front of it. So when we're dealing with kilograms, we tend not to use any other SI prefixes with it at all. So, for example, when we come on to gravitation and we look at the mass of the Earth, which is approximately 6 times 10 to the 24 kilograms, we would leave that as times 10 to the 24 kilograms. You definitely wouldn't start messing around and trying to say, trying to put it in terms of zettagrams or yottagrams or something like that. We just leave kilograms well alone. When it comes to seconds, if I choose green for this one, when it comes to seconds, we tend to only use the small number prefixes. So milliseconds, microseconds, nanoseconds are all absolutely fine. But again, we tend not to use kilo, mega, giga, etc. The reason being, when it comes to seconds and we get into bigger values for seconds, we can then start converting it into minutes, hours, days and years instead. So again, just a small note on that. Again, when it comes to meters, I'll do this in red this time. When it comes to meters, again, fine to use all of the small values, so millimeters, micrometers, nanometers, etc. We can use kilometers, or obviously kilometers, but again, when it comes to mega and above, again, with meters, we tend not to use those. The final note then on SI prefixes comes with the number that we use. Let's just imagine that we have some value which is 120,000. Let's choose a unit, let's have volts. Okay. Now, obviously, if we're going for SI prefixes, we've got a couple of different options here. We could obviously go for 120 kilovolts. I have seen some people try to say, well, that could be 0.12 megavolts. Now, both of those values say exactly the same thing. They will both give you 120,000, or obviously, if we're going to do that in standard form, that's 1.2 times 10 to the 5 volts. The one that would be standard practice is the 120 kilovolts rather than the 0.12 megavolts. The convention that we use is that the number that we've got here, we try to keep in between 1 and we try to keep it less than 1,000. If we go one step further and we have 1.2 million volts, okay, which obviously would be 1.2 times 10 to the 6 volts in standard form. Again, a couple of different ways we could do it there. We could either say 1.2 megavolts, or we could say 1,200 kilovolts. Again, by using the convention that we want to keep above 1 but less than 1,000, 1.2 megavolts would be the correct way of writing that. 1,200 kilovolts we probably at that point wouldn't use, and as I said, rather go for the 1.2 megavolts. So here then is a question for you to try. Through a resistor flows a current of 1.2 milliamps when the potential difference across the resistor is 240 volts. What is the resistance of the resistor? So at this point, please pause the video, have a go at the question yourself, and once you've got an answer, come back and resume the video and we'll go through it. So this hopefully should be a relatively straightforward question. The equation we're going to use is Ohm's law, which is V is equal to IR. We're calculating resistance, and therefore R is equal to V over I. When we put the numbers in, the potential difference is 240 and the current is 1.2 milliamps. So in your calculator you would do 1.2 times 10 to the minus 3. Now when you hit equals, my calculator tells me 200,000. Now we know that the unit is ohms. Now of course at this point we've got a couple of different ways that we can go with this. Firstly, let's do the standard form way. So 1, 2, 3, 4, 5. The answer should therefore be 2 times 10 to the 5. Now we've got to be extremely careful here. If we look at the question, we've got 2 sig figs for the current and we've got 2 sig figs for the potential difference. And therefore, to give this answer to 2 significant figures, we should say 2.0 times 10 to the 5 ohms. That would give us a 2 significant figure answer to match the question. If we'd have said 2 times 10 to the 5 ohms, now that would only be to 1 significant figure and would therefore be incorrect. It's the 2.0 times 10 to the 5 ohms that would be correct. The other way, of course, that we can go with this is to go down the SI prefix route, using the ENG button, which is of course an extremely useful button in order to do our standard form. We end up with 200 times 10 cubed on our calculator, and therefore we can write that as 200 kiloohms. Again, that would be a perfectly acceptable answer. Whatever you do, don't try and write that as 0.2 mega ohms. That would be probably marked incorrect at that point, because of course the number in front we want to try and keep 1 or above, and definitely not go to 1,000. So keep it 1 or above but below 1,000. So 200 fine. 0.2 mega ohms is not how we would do that answer. So in summary, in this lesson we've looked at 3 things. We've looked at significant figures, standard form and SI prefixes. So just to remind you then, when it comes to significant figures, always have a look at the question and try to match the number of significant figures to the question as far as possible. With standard form, remember, if it's 10 to the 3 or above, then we're going to use standard form, or of course if it is below 10 to the minus 3, we will use standard form as well. And then finally we looked at the SI prefixes and what they are and how to use them. Obviously, just as I said, be careful to make sure that 1 or above is absolutely fine, and we can go up to but not including 1,000 when we're using our SI prefixes. So that's the end of the lesson. Again, hopefully you found that useful. Thank you very much.